Welcome to the lesson video for principal components. In this video, we're going to talk about principal components, which are an important tool in statistical learning and data mining. So first, we're going to talk about what principal components are. So what are principal components? We have a plot shown on the right-hand side of the screen of a bunch of data points from a two-variable Gaussian distribution. And so the first principal component is going to be a vector, and it points in the direction of greatest variance. So on this plot, we have our mean right in the center, and then this line pointing up and to the right, that's going to be our first principal component, which we call PC1. It points in the direction of greatest variance, and its length is the amount of variance in that direction. There's different conventions. Sometimes you'll see a principal component being a unit vector in that direction. Sometimes you'll see it a vector with its length equal to the amount of variance in that direction. Each next principal component is going to point in the direction of greatest variance, which is perpendicular to all the previous PCs. And so in our plot on the right-hand side, the next principal component would be this red vector right there. That would be PC2. If we were in higher dimensions, we would have a PC3 and 4 out to the number of dimensions that we have, and the length of each principal component is going to be the variance in that direction. If you remember the multivariate Gaussian distributions that we've been talking about, they have these level sets, which are ellipses or contours, right? And these help us picture the multivariate Gaussian distribution in two dimensions. Your data is more likely to be in these inner ellipsoids than the outer ellipsoids, and you think about the distance to the outer ellipsoids acting somewhat like a z-score. The principal components give us the axes for these ellipses, so they're connected strongly to the multivariate Gaussian distributions. How do we use principal components? Well, the first few PCs give us a subspace containing most of the information. This is important because then we can use the first few PCs as a new set of features. This is called dimension reduction. It's generally true that if you can reduce dimension and you get rid of dimensions that don't have information in them, those dimensions where the variance is low, then your algorithms will work better. And so we can use those first few PCs as features to give us better predictions, and we can take high dimensional data and use those first few PCs to get scatter plots so we can visualize structures in high dimensional data. Now, if you understand what we've talked about on these first two slides, you understand most of what's needed for principal components in statistical learning and data mining. We're going to go a little bit into the math that goes into computing principal components and showing that these properties that we've just talked about, pointing in the directions of greatest variance and so on, that these are true, that support these claims. If you understand or you've had exposure to more linear algebra, matrix algebra, the computations make a lot of sense. But whether or not you understand the computations or have the experience in linear algebra matrix algebra, the math will provide a lot of understanding into the principles that are underlying principal components and how we use them. So first thing to talk about when we get into the underlying mathematics is review the dot product in vector projection. And so in this example here, we have a vector A, we have a vector B shown in blue. I'm going to take the projection of A onto B, and that's the vector that's shown in green, and the length of that vector is what we're going to call L. And so the length L can be computed by taking A dot product B and then dividing by the magnitude of B. So that's what we call vector projection. That green vector is the vector projection of A onto B, and its length we call the scalar projection. If B is a unit vector, then the length L is just A dot B. We don't have to divide by the magnitude of B because that magnitude of B is 1. And so L is called the component of A in the direction of B. So if we want to project onto a subspace, we have 4 red data points here that we're showing, and we have a blue line which represents our subspace that we want to project onto. What we do is we get a unit vector that's going to span our subspace. It's a one-dimensional subspace, so we only need one vector to span it, and we'll call that B. And then for each data point A in our data set, we're going to compute the distance A dot B, or in matrix notation, A transpose, then matrix multiplied by B, and that will give us this new point shown as the blue dot in the plot, which is the point in this subspace that we've projected A onto. And we can do this for all the points, and this gives us our projection of our data into the subspace spanned by B, or into the subspace, which in this case is just a line. We can do this a little bit more concisely with some matrix algebra notation. So if X is our data, right, so X is a matrix, each row corresponds to an observation, each column is a feature, and blue is our unit vector, then the projection of the data is just A, it's just X multiplied, matrix multiplied by B, shown here. And remember, B is a column vector, and X is the array where each row is an observation. And that gives us our projection that we talked about previously. So let's look at a projection on some interesting data. So here in the left-hand plot is a figure from a book. The book is shown on the bottom left-hand side of the screen, reference. So these are 3 classes of a data set, and the data set lies approximately on a sphere in 3 dimensions. And so we're going to use PCA to view this data set in a way that will make more sense to us than looking at it as it's shown in this figure. So in the center box, we have our data set again, blue, red, green, and we have the 2-dimensional subspace spanned by the first 2 principal components. And so the mean of our data set is in the center of that plane, right around there. The first principal component points in approximately that direction, and the second principal component, right, that's the direction of greatest variance perpendicular to the first, points approximately in that direction. And I guess the first principal component, actually, I drew it pointing the wrong direction. It points that way, not this direction. And so over here on the right-hand side, we have a plot of our 3 classes in the plane. And the first principal component is now there, and the second principal component is there. So we've taken these 2 principal components as our new basis for the data. In that plot on the right-hand side, you can see the data much more clearly. You see we have reasonable class separation, and this might be a nicer place to do training with algorithms versus the original plot in 3 dimensions. This gives us a nicer way to view this data set. If that original plot on the left-hand side, right, this plot with 3 dimensions of sphere, if that was in, say, 10 dimensions, it would be hard to see the data and understand. So using the first principal components would give us a much nicer way to view the data. Okay, so how do we compute the principal components? So let's talk about doing a little bit of computations that would be needed to compute the principal components in R. We have R. R will do all these computations for us, but it's nice to at least see the formulas that go into these computations. And so single variable, the expected value of y is given by the formula in the box, 1 over number of elements times the sum of y over all y in our data set. And so the mean right here is given by the expected value. Mean is the expected value of x, and so standard formula for taking the mean or the average value in our data set. This is a single variable data set. The variance right here, it's the expected value of x minus the mean times x minus the mean. We usually write it just x minus the mean squared, and then it's given by this standard formula for the variance that I'm sure you're familiar with. So to do the same things with multiple variables or with vectors, we're going to have the same notation for expected value for an n-dimensional random variable. And so here, remember, our x represents our n-dimensional variable. It's a column vector, and its components are x1 through xn. The mean is just going to be the expected value of x, which we write mu, and it's a column vector with mu1 through mu n. Just a comment on notation for us and for the textbook. We won't always put a lot of effort into showing these things are vectors. So mu is the mean of our data set, and it's a vector. Sometimes in physics you'll see arrows on top or bold or different notations to point out that that's a vector. So covariance matrix, sigma, we've talked about the covariance matrix. We gave a formula for it at one time in a previous lesson video, and so here we're going to see a little more where that formula comes from. So sigma, it's the variance in x, and so we take this formula for expected value that's going to give us the variance, and that looks a lot like the single variable formula. So compare these two. The only difference is that in the multivariate, they're vectors, and we have this transpose on the second one. So what that transpose does on those vectors, when we do matrix multiplication, the transpose says we have the first x minus mu as a column vector, and the second x minus mu as a row vector. And then when we take their matrix multiplication, we get this matrix or this array that we have shown here. And if you look at this, this is our what we call our taking the average value, right? We still have the expected value. We add up these for every I, xi in our data set, and then we divide by the number of data points minus 1. And if you look at what we have here on the diagonal, we have the variance for each of the individual variables, feature variables. And the off-diagonal terms are the covariances between the different feature variables. And so the covariance matrix rolls up or includes all the variances and all the covariances between all possible combinations of our feature variables. Okay, so definition. A vector V that's a solution to this equation, which is a matrix sigma times V is equal to a scalar lambda times V, is called an eigenvector, and the associated value lambda is called the associated eigenvalue. So this is a definition of an eigenvalue from linear algebra. And another definition, the eigenvectors of the covariance matrix are called the principal components. And so this is one definition for principal components that allows you to compute them from data. Right, we often take principal components as the vectors that point in the direction of greatest variance, which is an okay definition, but it doesn't tell you how to compute them. This definition that we have now on the screen tells us how we could compute them. So there's an important connection here. The eigenvalue, the kth eigenvalue, is going to be the variance in the direction of the kth principal component, which is the kth eigenvector here, which we're calling UK. So here's a proof of this statement, that these eigenvalues give you the variance. So for a unit vector u, right, when we say unit vector u, we mean this is true. U dot product itself is going to give you 1. The variance in the direction of u is given by this formula. So here's just the definition of the data in the direction of u. We take that dot product of the data onto u, and we put that into our variance formula. And so it's the expected value here. Now we've taken this u inside the formula and we've brought it out. That's because that dot product works nicely with our unit vector u, and so you can bring it through the expected value. Now we've taken the two u's that are inside and we've brought them before and after. Then a little bit of linear algebra says that that's how that works. And then this piece inside, right, this is exactly the formula for a covariance matrix sigma. Okay, so we use this little thing that we've just shown in a computation, that variance in the direction of x is equal to variance in the direction of u is equal to u sigma u, and that is what we're using for this first equality. So if uk is the kth eigenvector or kth principal component, then the variance in the direction of uk. So now we're going to compute the variance in the direction of the kth eigenvector. And so by the computation we did above, that's uk times the covariance matrix sigma times uk. Now because uk is an eigenvector for that covariance matrix, we can replace that sigma by a lambda, right? This piece here becomes lambda uk by this formula. It's the definition of an eigenvector. We can swap the order of operation here because it's just a scalar multiplying a vector, and then uk times uk is 1, and so we get just this lambda. And so that says the variance in the direction of the principal component is equal to the eigenvalue associated with that principal component. Right, that's the thing which we were to prove here. Okay, so the eigenvalue is the variance in the direction of the principal component. Okay, so let's use this on some data. So we've walked through a little bit of the underlying math just to see how some of the things work with principal components, how the computer is computing them. Let's walk through some examples. And so what we're looking at here is Zipcode Data. It's a data set with a large number of handwritten digits, 1 through 9. This is a kind of a standard common test data set. And what we're showing are 130 examples of handwritten threes. And so the way this works is number 3 is written, and then there's a digital image of that number 3. And what we're looking at are 130 digital images of the number 3. And each image has 16 rows and 16 columns of pixels. There's 256 pixels in each of those images. And so we have 256 features. Each pixel is a feature. And so we treat each of these little images of a 3 as a feature. And so we're going to apply principal components analysis to this set of 3s. And so in the Zipcode data, there's 1 through 9, and the goal is to look at these different images of these different handwritten digits so that a computer can automatically tell what the person has written, so that the computer can read the zip codes on mail and sort it quickly at a post office, for example. Okay, so we've taken this data set of 3s, and it's in 256 dimensional space. We've computed principal components, and now we've computed the projection onto the first 2 principal components. And so the first principal component points in this direction, and the second principal component is pointing in that direction. So we've projected onto the plane, 2-dimensional plane of that data. And so you can look at the data after it's projected in the plane. And so there's a grid of circled data points, and this grid of 3s, and these grid of 3s on the right corresponds to these data points. So for example, this data point right here is that 3. This data point is this number 3. This data point is that 3. And I guess this one here is this 3 here. So if we look at the left-right variation in the 3s, that's the variation captured by our first principal component. So our first principal component points in that direction. And so if you look at particularly the top row of 3s, and you look what's different among the top row of 3s, you can observe that it looks like the length of the extensions on the top and the bottom of the 3 vary from left to right. And this is kind of true as you read across any row in those 3. So the first principal component seems to be capturing the extension on the top and the bottom of the 3, or the width of the number 3. If we look in the vertical direction, this is the vertical direction is given by our second principal component. You'll see at the bottom row of 3s, those are written in a very thick ink or a very thick pen. At the top, they seem very thin. So the second principal component seems to be capturing the thickness of the 3s in our writing. And so here's another way to think about that or to view that. So here's that same plot as before, and now shown below we have f hat, or the prediction applied to lambda. Lambda would be a data point after it's projected into the first 2 principal components. It would be the mean value, and then lambda 1 times the first principal component plus lambda 2 times the second principal component. And so these plots here give us a way to view the 2 principal components. Remember, the 2 principal components are vectors in 256 dimensional space. We can show those as an image, like these are images created from those vectors, and you could see in this first principal component there's kind of a blurring in the length of the ends of the 3, and that corresponds to what we observed before. The first principal component captures the width of the 3, or the extension on those, the upper and lower arms. The second principal component here seems to be capturing, there's a blurring in the thickness of the letter that may be capturing the thickness of the number 3, or the ink that's used to write the number 3 with. Maybe that's clear in that second principal component, maybe not. At any rate, we've taken our 256 dimensional data set, which is the numbers 3's, and we've projected it in 2 dimensions, and we can see some of the structure that's present. Now, one of the questions that have come up is how many principal components do we want to use? In that example of the 3's, we went from 256 dimensions down to 2, just because we can easily view things in 2. But maybe there's more information in there that we want to understand. And so this quantity in this formula, it's the sum of the first k eigenvalues divided by the sum of all the eigenvalues. That ratio tells us the fraction or percentage of total variance that's contained in the first k principal components. So often, right, so here we have p total principal dimensions, and we're going to project down to a subspace of dimension k, which is less than p, and the amount of information that we retain is given by this fraction here. It's the sum of the eigenvalues for the principal components that we're keeping divided by the sum of all the eigenvalues. And so it can be used to estimate how many principal components that we want to use. Sometimes people will say, I'm going to use enough principal components to keep 90% of the information, for example. In those 3's, we would need 50 principal components to account for 90% of the variation. And if we just use 12 principal components, that would account for 63% of the information. So that gives us some sense of how much information we're keeping as we project down. So general PCA or principal component analysis principles. First, as a common rule of thumb, if you're going to compute n principal components, you should have at least n squared observations. There's other things that will increase the number of observations you need higher, but this is just a back of the envelope type of estimation people use. You should understand the interpretation of the PCs, that the first few PCs give you the directions of greatest variance. And plotting, another thing that's important to remember, plotting against the PCs, or the projection into the space spanned over the PCs that we looked at, it shows the variance in the data, but it doesn't always show you class separation. Another thing that's interesting to know about PCA, if the data has a distribution close to a Gaussian normal random variable, then the PCA plot, that projection will look round and normal. So if you remember, the multivariate Gaussian distributions have those ellipsoids. When you project down in the principal components, those ellipsoids become circles. PCA and the covariance matrix, they're useful as a larger computation for other methods, so anomaly detection, classification, target detection. So these are underlying mathematical tools for a lot of different methods. So these can be used for noise reduction in digital images or in sound, as well as dimension reduction. Let's look at another example. So this is a visualization of ethnic groups by RNA. So the data is 2,654 observations from 16 different ethnic groups, so 2,654 people. For each person, there is about 186,000 single nucleotide polymorphisms, SNPs, which are distinct genetic variations. So these are switches in genetics that can be measured. So there's 186,000 features. That's a very large number of features. And so this is a high dimensional data. It's 186,000 dimensions. So we definitely want to be able to look at it. We'd like to be able to look at it in lower than 186,000 dimensions. That's hard to visualize. Being facetious, right? That's impossible. I don't understand how you can visualize it. But, so we take the principal components, compute your PCAs, and then this list right here is the eigenvalues, the top 10 eigenvalues, or the eigenvalues for the top 10 principal components. So one thing you'll notice here, the top couple seem to contain, I'm not sure where to draw the threshold, maybe the first 4 contain a lot of the information. I'm not sure how they trail off as you go down the list, but at least the first 2 seem fairly significant. 178 and 118, large. Those are fairly large compared to the 10 and below as you go down the list. And so we apply PCA to this data, meaning we compute the first some number of principal components then we project the data onto the first two. And if you look at this picture on the right-hand side, this is the projection of that data from 186,000 dimensions down to 2 dimensions using principal component analysis. And we've colored the data points for people in the different ethnic groups, and you can see there's a really nice structure there that connects the different regions somewhat geographically. And this is something that people use to study the genetic relationships between groups, maybe where people have traveled from or where societies have colonized from and to over time historically. And so there's some connection and structure that we can understand here. That's provided by the principal components. The big takeaway here is we've gone from 186,000 dimensions down to 2 dimensions, and now we're able to visualize something that wasn't possible to visualize in the full dimensional space. Here's another application of principal components visualizing similarities in wine groups. And so this is a fairly standard plot that's given in R. And so we have 178 observations, so 178 different samples of wine, and then for each sample of wine we've computed 13 features. So the features that have been computed, or the attributes, are in this list here: alcohol content, acid content, ash, alkalinity, magnesium, and so on down through the list. And so we've computed the first 2 principal components, PC1 and PC2. And so PC1 has 36.2% of the explained variance. So the first eigenvalue divided by the sum of all the eigenvalues, that's 0.36. So we have 32% of the variance, or 32% of the information. The second PC is 19.2. So what we have here is a total of 55 or so percent of the variance is present in this data. And you could see our groups, the blue, and the green and the red, and those correspond to 3 different types of wine, from 3 different cultivars. And so here's in this paragraph on the left, these data are the result of chemical analysis of wines grown in the same region in Italy, but derived from 3 different cultivars, meaning cultivars are grapes. So there's 3 different types of grapes, and we can see how those different types of grapes give us clusters in this PC space. One of the things that R does that can be handy is it plots in this PCA space. You can see on these plots these orange vectors that go out and give you the projection of the different features. That's like the unit vector in the direction of that feature variable projected into principal component space. So it tells you somehow some sense of how the features group together according to those principal components. So review. Each PC gives a direction of the next greatest variance. The PCs, or the principal components, they're the eigenvectors of the covariance matrix, and the eigenvalue for each PC is the variance, the direction of that PC. The fraction of information contained in the projection on the first few PCs is given by this formula here, and it's the sum of the first k eigenvalues divided by the sum of all the eigenvalues. And the PCs are useful for improving prediction performance, right? We can do dimension reduction, just take the first few principal components and run our algorithms there as opposed to trying to run our algorithms on the data in its full space. That improves performance. And they're also useful for visualizing high dimensional data. Thank you very much.